Gdansk, and he's going to be telling us about his Witworld GPT, which is specialized for post-quantum theory. So over to you, Paulo.
Okay, thank you, Vicky. Hello, everyone. I hope you're all doing well. And my name is Paulo Cavalcanti. I'm from ICTQT in Poland. And in this presentation, I'm going to answer this question. Given that post-quantum theory exists mathematically, can it be realized by some conceivable physical theory? And to answer that, I will just make it more mathematical in that way. Given that post-quantum theory exists mathematically, can it be realized by some generalized probabilistic theory, or GPT? And why GPT? Because states, they capture the idea of preparations, effects capture the idea of measurement outcomes, and transformations, they capture the idea of change. So the GPTs, they have the form of theories that talk about physical experiments. So because of this, the form of this presentation will be the following. I will first give you the GPT conventions that we use in this work. Then I will give you a brief introduction to steering, going from the locality and making a comparison by using the diagrams of the GPT framework. Then I will show you how we build a theory that a GPT that can realize post-quantum theory, and this will give you the answer by example. And then I will use Witworld, the theory that we built to uh, investigate the information processing capabilities of post-quantum theory. So in the diagrams that I will show to you in this presentation, we have four types of wires. The simple wires, they are going to represent classical systems. The double wires, they represent quantum systems. These ladder-like wires, they represent Boxworld systems. And the thick wires, they represent general systems of the GPT. So for example, they can be this wire combined with this wire, or this wire combined with this wire, or just this wire, or any general wire of the GPT. And every time I draw a diagram, time is flowing from bottom up. So it's the opposite convention that some people use here, but from bottom up. So to introduce you to steering, I'm going to start from Bell scenarios in the GPT framework. So a Bell scenario in a GPT is given when all parties in a multi-partite experiment, they make measurements on some shared resource S. So here, for example, Alice chooses measurement X and gets outcome A. Bob chooses measurement Y and gets outcome B. And this diagram will give you will give you a conditional probability distribution, and we call it a box. So for Bell non-locality, the fundamental object of study is called a box and is a probability conditional probability distribution. So if we are in the GPT framework, we can ask how can you write this resource S. So if you can write the resource S using only elements of some GPT, then what this means is that you can realize that box on that GPT. So uh, for example, Bell's theorem, in, you, speaking in that context, Bell's theorem says that some of those boxes, they are realizable in quantum theory, but they are not realizable in classical theory. And it is also known that some boxes, they are post-quantum, that is, they are not realizable in quantum theory. So no matter what pieces of those you take from quantum theory, you cannot realize those assemblages that are no signaling. And by no signaling, I mean consistent with relativity. So continue with this diagram language. The parallel between steering and Bell non-locality becomes very clear, because now we have a scenario, a multipartite scenario, which is more or less the same, except that there is no choice being made by Bob. And on his side, he just keeps a quantum state. So a steering scenario is given in a multipartite experiment when one of the parties doesn't make any measurements on the shared resource, and he just keeps a quantum state. And in this case, the fundamental object of study is called an assemblage. That is a set of subnormalized states. And subnormalized because the norm of the state will give you the probability of that state happening, and the label will give you which state is happening depending on the choice of Alice's measurement and the outcome that she observes. And then we can uh, also keep saying that in the GPT framework, some assemblages they will be realizable in some GPT and some will not. Uh, so similarly to correlation, some assemblages are realizable in quantum theory, but they are not in classical theory. And moreover, there exists post-quantum theory. This has been proved mathematically. Now, for this example of post-quantum theory, if you want to see a post-quantum theory, you need to go to more general scenarios. In this simple bipartite scenario that I drawn here, you cannot find post-quantum theory. But, for example, if there is some choice of classical variable y that Bob can make to influence the resource, then you can find some assemblages which are not realizable in quantum theory. And also, uh, another example of a scenario where you can find post-quantum theory is when Alice sends her output, the output of her measurement to Bob. Then Bob just inputs that information to his part of the resource, and then just keeps the state. These are two examples of scenarios, but where post-quantum theory can happen, but there are more. For example, if you have a multipartite scenario, like tripartite, then you can also observe um, post-quantum theory even without these inputs for classical inputs for Bob. And then we can just extend the questions that we were making. So, can every no signaling correlation be realizable by quantum theory? No, because no signaling doesn't signal out quantum correlations. Can post-quantum correlations be realized in some GPT? Yes, Boxworld realizes them all. And Boxworld is one example of a GPT that exists in literature. Can every no signaling assemblage be realized by quantum theory? No, because post-quantum assemblages they exist mathematically. And now, finally, our question: can post-quantum assemblages be realized in some GPT? We will answer by the construction of Witworld. So Witworld answers the last question in the affirmative. And to define it, we need to define the system types and the valid states for each system type in the theory. We need to define the composition rule for system types. We need to define the valid effects for each system type and the transformations that you can have in the GPT. So let's go and see how Witworld is defined. Basically, what we have is three types of simple systems, which we call atomic systems. And these three types are classical systems, where the valid states are just probability vectors of a single probability distribution. Boxworld systems, where the states are probability vectors which contain lists of independent probability distributions. And quantum states, where the states are the usual unit race operators on Hilbert spaces. For example, a classical state could be just this probability distribution. A Boxworld state in the of dimension 2, 2. And notice that this is not just one number as you have for classical uh, and for quantum system, but it's two numbers. You have one probability distribution and then another probability distribution, and they are independent. Or example of a state of a qubit. And then the more general system types in which world they are simply built by combining those systems through the combination rule that we will define later. So for the atomic systems, we also need to define the effects. So the rule is very simple. Any function that takes states to a number between 0 and 1, which is just a probability, is considered a valid effect. So for those three atomic system types that we defined, This simply recovers the effects from classical, from Boxworld, and from quantum theories. Now, to combine those three types of atomic systems into more complex system types, we will just use this rule that is called the maximal tensor product. And it's maximal, assuming local tomography, because the set of states of the combined system A and B is simply the largest one in the product vector space that is consistent with separable effects. Maximal because the separable effects, they are the simplest effects that you expect to see when you combine systems. That is, you don't get extra effects by combining systems, you just have the effects that you had before. And then you make the set of states the largest one, which is consistent with these simplest effects, consistent in the sense that any separable effect when applied to the vector that is a state will give you a probability, a number between 0 1 or a probability for all separate effects. Then this means that the vector is in the um, state sets of the combined system. And for these more complex sets, we simply extend the rule that we are saying using before for atomic systems, and we say that the set of effects for any system in Witworld is simply the largest one that gives probabilistic predictions, given our choice of composite state space. So this rule is called the no restriction hypothesis. No restriction because you are not you are using the largest set of effects that you can um, imagine for the set of states. And finally, uh, for this allow transformations for those systems, we again choose the largest set, which makes sense given our choice of composite state space and effects. And here, makes sense, by making sense, I mean that any transformation that will always take uh, states from one system type to states of another system type, even when you compose it with another uh, system C, for example. Um, if this always happens, then you have this transformation to be allowed. So together with the no restriction hypothesis, this constitutes what we call the generalized no restriction hypothesis. So we have both the larger set of effects and the larger set of transformations as the effects and transformations in Witworld. So put shortly, Witworld is a GPT which contains classical quantum and Boxworld systems, combines systems through the maximal tensor product, and satisfies the generalized no restriction hypothesis. Now, some interesting properties of Witworld is that the use of the maximal tensor product to combine systems implies that the theory has only separable effects, and there is no difference between positive and completely positive maps in the theory. And moreover, when you combine two quantum systems, what you obtain of dimension d and d prime, what you obtain is not a quantum system of dimension d prime. This is because the maximal tensor product is not the combination rule for quantum theory. So this the set of effects, the set of states that you get when you combine quantum systems is larger than the set of quantum states when you use the combination rule from quantum theory. And in that largest set, you have every entanglement witness as a state. And this is why we use Witworld for the name of the theory. Uh, Post-quantum assemblages, they can be realized, and this is, I will give you some examples shortly. And it can be shown that post-quantum theory is stronger than quantum resource by just using diagrams from Witworld. So let's start seeing the examples of post-quantum theory. In particular, you you can notice that we have all the states of Boxworld, and the combination rule from Boxworld is the maximal tensor product. So this means that Boxworld itself is a subtheory of Witworld in the sense that if you restrict the theories only to systems that are Boxworld type, then you obtain the complete with Boxworld GPT. So we can use this capacity of Boxworld to realize the PR box we can leverage this capacity to produce post-quantum theory in Witworld. So if you take these effects AX, where 00, 10, 01, and 11 are given by these vectors to define this measurement in Witworld, and you take this state that we call SPR given by this vector, then you can realize the PR box in quantum theory in Witworld through this diagram where the parties that share this SPR state, Alice chooses X, Bob chooses Y, Alice takes outcome A, Bob takes outcome B, and the conditional probability distribution is just the one from the PR box. So using those diagram elements, we can construct a post-quantum assemblage where the outcome of Bob, instead of just being read as B, it's input to a controlled preparation of the of either the state 00 or the state 11. If you make this construction, you can prove that this resulting assemblage is post-quantum and is realizable with world. Um, okay, so this is one example where post-quantum theory appears, but leveraging the PR box, the realization of the PR box. But we can also have post-quantum theory without the use of the PR box. And to go there, uh, we can use this lemma where in GPTs where the transformation rule is the maximal tensor product, every positive transformation is also a completely positive transformation. So by using this lemma, we can say that taking the partial transpose of quantum states is allowed in Witworld, although it's not allowed in quantum theory. And then we can use this partial transpose to produce post-quantum assemblages. So take a controlled transposition of quantum states here, where the transpositions happen or doesn't happen depending on this classical input. You can construct this diagram in Witworld where Alice and Bob uh, they share a Bell state. Alice chooses to measure either sigma 0, sigma 1, or sigma 2 as the Pauli measurement and get some outcome. And Bob chooses to either uh, perform or to not perform the partial transpose. The resulting uh, the resulting assemblage is post-quantum and is realizable in Witworld, but not in quantum theory because of the realization of this transposition of quantum states here. And using the lemma, this second lemma, that says that in Witworld, every quantum entanglement witness of the combined system QD with QD prime is a valid state of QD prime. Uh, then we can produce assemblages, which are just like quantum assemblages, but have entanglement witnesses as states. It has been proven that some of those assemblages are post-quantum, and they can be realized here because every piece of the diagram is a piece of Witworld. So now that we know that Witworld can realize post-quantum theory, we can use the diagram here to investigate the information processing capacities of Witworld. So I can show to you that post-quantum theory is a resource stronger than quantum through for this task of remote state preparation. So remote state preparation is a protocol where Alice wants to remotely prepare a state in Bob's lab. But although this looks like teleportation, it's not the same because if you see here, there is no part where you see joint measurement, and the state that Alice is sending must be actively encoded by her through some unitary on the shared state that she has with Bob. So the optimal quantum protocol is Alice just encodes her states through the unitary, performs a POVM, sends the result, a POVM on her part, then she sends the result of her measurement to Bob, and then Bob makes some unitary operation to his share of the system, depending on the message, to recover the state deterministically, to prepare the state deterministically. Uh, Now let's see. In quantum theory, the optimal efficiency in this task is that Alice has to send 2 bits of information to Bob to have success in the task. But in Witworld, we can use the universal NOT gate, which takes any quantum state for a qubit, takes any quantum state to his to some state that is orthogonal to it. Uh, this this operation can be realized in Witworld, but it cannot be realized in quantum theory because it's not completely positive in the sense of quantum theory. So taking a controlled universal NOT gate that performs or not the universal NOT depending on this classical input, together with this unitary to encode the state that Alice wants to prepare in Bob's lab, and this measurement in the 0011 basis, you can construct this diagram for a protocol in Witworld, which achieves success deterministically with only 1 bit of communication, outperforming the quantum bound of 2 bits. Now, one of the scenarios of steering is the instrumental scenario. And if you see a diagram, if you remember the diagram of the instrumental scenario for steering, you can see that this diagram is simply a diagram of the instrumental scenario. So if the protocol has a diagram of post-quantum steering and it's outperforming quantum theory for this task, it means that the resource for this task is post-quantum theory. The stronger the quantum resource is post-quantum theory. So this is the first instance where post-quantum theory is shown to be stronger the quantum resource for information processing. And we realize that only by looking at the form of the diagram. So to conclude, uh, from this presentation, we can see that we answer in the affirmative the question of whether there exists a conceivable physical theory which realizes post-quantum theory, and we do so by explicit construction of an instance of that and call it Witworld. We built Witworld by providing a scheme for combining features of different previously known GPTs, namely classical quantum theory and Boxworld. And we use the diagrammatical reasoning to prove that post-quantum theory is a stronger than quantum resource for an information processing task for the first time. If you want to see more details, you can find this work in archive. And I will leave some open problems here. So we know already that information processing is that post-quantum theory is a stronger than quantum resource for information processing, but it would be interesting, for example, to know uh, if it can be stronger than quantum for more complex tasks. For example, instead of preparing 1 qubit, what if you prepare Q-treat or uh, more less simple states in Bob's lab or any other kind of task. And another question that still remains is, does this GPT with world realizes every post-quantum assemblage? We know that it realizes many of the analytic examples that we have in the literature, but we still don't know if it can realize every post-quantum assemblage. It's possible, but we're not sure. So with this, I finish my presentation and thank you for your attention.